Okay, so section 6.1b, we are going to continue with our discussion of discrete random variables for a bit, and then also jump into the concept of a continuous random variable. In the last video, we talked a lot about expected value for an discrete random variable, and that was basically doing an average. We also want to have a way to measure the spread of a random variable, which is going to be our good old friends, the variance and the standard deviation. So we can calculate this on a probability distribution in a table or off of just any random variable that they give us. And the formulas for this are on your formula sheets. I didn't show it last video, so let me pull that up now and show you guys where that's located. So on your first page right here, there's a section for discrete random variable, and then you see the mean expected value formulas that I gave you. They used a slightly different notation, P of xi instead of just pi, basically same thing. And then they have the standard deviation formula written down right here. So I'm going to copy this down on my slides in just a second. But before I do, let's just talk about what this is saying here, because you guys already know how to calculate standard deviation. So xi is a value. So you're still taking the value minus the mean, like we would do normally, and squaring it. And then you're going to be adding them up and taking a square root, just like you usually would do. The only difference is instead of that divide by n minus 1 step, you get your division taken care of by multiplying each of those terms by the corresponding probability. So it's going to be very similar to how we would find standard deviation in the past. And let me go ahead and write that down here on our slide. So for the variance, there are two options for symbols. You could write variance of x like this. That's a thing that people do. Or our symbol for variance, it's our standard deviation symbol with a squared on it and an x. And let's repeat how you would actually find that again. You're going to be adding up a bunch of stuff, and you add up each value minus the mean. You're squaring it, and you're multiplying by the probability of that value. Our book uses just pi, but since our formula sheet has probability of xi, that's fine too. So you take each value, subtract mean, square it, multiply by probability, add them up. And the standard deviation can either be SD of x or just sigma of x. And it's going to be the same thing, but with a square root on it. So yeah, that's our basic setup right here. And this formula should hopefully make a little bit of sense to you guys how it works. And then how to interpret the standard deviation of a random variable. We've done this before, but you talk about the typical distance. So for a randomly selected variable, a randomly selected value, so for a randomly selected value, we expect it to vary from the mean of blank by blank. So basically, we're just saying, like, if the standard deviation is 3, a randomly selected value will typically vary from the mean of whatever by about 3. You guys already know how to interpret a standard deviation from chapter 1, and it's not that different in the context of random variables. So let's do an example problem where we actually practice here, looking at two different kinds of bets you can make in a game of roulette and how you would actually calculate and interpret their standard deviation. So we need to calculate our standard deviations here and see which one is bigger. But before I actually make the calculations, you should be able to look at these tables and decide which one will have a larger standard deviation. So look at the values that are possible for the red black. You can either lose $1 or get $1. And look at the values that are possible for the corner bet. You can lose $1 or gain $8. Which of those, if we list out a bunch of negative ones and positive ones, or negative ones and positive 8s, which one is going to vary more on average from the mean? You should be able to give me an answer for one of those two. So think about what that would be. And it should hopefully be that this corner bet has a larger standard deviation because the values are farther apart. There's going to be more varying from the mean of whatever it is. So if you're going to calculate a standard deviation, you have to know the mean first. So let's say X is going to be, always a good idea to define your random variable when you start. It's going to be the net gain from a red-black bet. And I'm going to make Y the net gain from a corner bet. They told us in the problem both of these variables have the same expected value. And if you remember from the last video, it was like -2 over 38 was our mean. So the mean of X and the mean of Y are both -2 over 38. So let's find the variance for our first bet right here. So we're basically just plugging and chugging using a formula. And the way that you do that is you start out with each value. So my first value is a -1. I subtract the mean of -2 over 38. So minus -2 over 38. I'm going to square it to make sure I get a positive quantity. And I'm going to multiply by the probability of that outcome. This was for the -1. So I'm going to multiply by 20 over 38. This guy will be like the piece I get from my first one. And I have to add up the different terms. So I'm also going to have a piece for my second term. My second term is going to go +1 minus my mean. I'm going to square it. And I'm going to multiply by my probability for that one. So let me go ahead and calculate that guy. You pretty much, after you write these down, are just going to type them in the calculator like they look, which is a little bit tedious to do, admittedly. Later on in this video, I'm going to show you guys how to do the like an even shorter way. So there is an easier option than this, but it's good to know how. If I type all that in, I got 0.997. For this guy. And that means if I want the just standard deviation, that was still the variance, I just take the square root of what I just got, which gets me 0.999 if you round it. So how would I interpret that value? That was for my red-black bets. So on a randomly selected red-black bet, I would expect the amount that I win to vary from the mean of -2 over 38, which was -5 cents, for it to vary by a typical amount of 0.999. So re-summarizing right here, on a randomly selected bet, the mean is about -5 cents. So I would expect a randomly selected bet to vary by about $1 from the mean of -5 cents. Okay, so go ahead and try to calculate, pause me and calculate your standard deviation for the second guy right here. I'm going to pause the video and come back with just an answer for that one. All right, so there's a lot of writing on this page right here. We've got the old answer from before in red, and we've got our new one in blue. And the new standard deviation is 2.76, which is quite a lot higher than the other problem of 0.999. Again, whenever we do standard deviation, I'd like you guys to have an intuitive idea of what is going on. Let's talk about why it makes sense numerically that this would be a bigger number than the red problem. So over here, I have a red data set. The mean is -5 cents. I'm going to have a bunch of negative ones. I'm going to have a bunch of positive ones, maybe a little more negative ones than positive ones, but I'm just going to have a bunch of those two numbers. The negative ones are about 95 cents away from a -0.05. So I have a bunch of 95 cents distances. And the positive ones are $1.05 away from -0.05. So I have a bunch of 95 cents and I have a bunch of $5s. And if you average those distances that each value is from the mean of -0.05, it averages out to about $1. That seems fairly reasonable. Okay? On the blue data set, though, I have a bunch of -1s and I have a less popular +8s. Well, the negative ones are 95 cents away from negative 0.05. The 8 that pops in there every so often is like, what is that, 795 away from the mean? No, 805 away. So if you average all those 95 cents and then the random 805, it makes sense that they vary more on average from the mean. So that's what's going on with standard deviation. So that is not very fun to calculate by hand. So there is an easier way to calculate standard deviation just by using your calculator. So if you guys have your calculators handy, or if not, just follow along right here. Really, our favorite menu on our calculator is the Stat Edit menu. And what I'm going to do is I'm going to punch in the values right here. So I have 1 through 5. This is for number of languages that somebody speaks. And then I'm going to put the probability that goes with each of them into the second column. So values in the first, probabilities in the second. And we're going to go to our favorite friend. We've used this menu before too, one variable stats. Now, when you do a one variable stats, the numbers that I actually got, the values I would record in the problem are in L1. Frequency list is something we have always left blank, okay? When you have probabilities attached to your values, you need to use the frequency list. So my frequencies are in L2. So normally, if it's just a random data set by itself, you'll want L1 and frequency list blank. But if you have probabilities, you need your probabilities in L2 for the frequency list. So if I calculate this right here, it's going to give me my mean. That's X bar at the top. So X bar is 1.457. I'm going to write that down. They write it down as an X bar, but I'm going to write it down. They don't know if it's a sample or a mean in the calculator. This is the actual mean of my data set is 1. Already lost it. I think it was 457. And then let me get my little calculator back. The standard deviation for this problem, they'll have it under sigma here. You can see that S is blank, is 0.671, if I round that. It's 0.671. All right, so you can get that info off of the calculator, which is going to be so much better and easier than having to calculate it yourself. But if this was on the AP test, they're not going to give you work for, oh yeah, I just did this just by using my calculator. So what you have to do is show a little bit of work. Like if I was going to do this, I would write down, I have the square roots. My first value is a 1 minus my mean squared times the probability for 1 plus I would do the same thing with 2, my second value, minus the mean squared times the probability for 2 plus ... So show a little bit of work before you just write down an answer. Okay, so that is the end of the standard deviation section of today's notes. We are transitioning now to the idea of a continuous random variable as opposed to a discrete random variable. And I already made this distinction last video, but a continuous random variable has no gaps between possible values. In other words, your possibilities are anything on the continuum here from the lowest possible to the highest possible value. You can have however many decimal spots you can get, basically. Examples of things that are continuous are like length, time, weight, etc. All right. So this next thing right here is a little bit confusing, a lot confusing for kids. And it's this idea of a continuous random variable equaling a certain value. So is it possible to have a shoe size that is equal to 8? The answer to that is yeah, absolutely. When you measure shoe sizes, shoe size is a discrete random variable. You're a 7, or maybe you're a 7.5, or you're an 8, or you're an 8.5. But there are specific gaps between these right here. This is discrete. It is definitely possible to have a shoe size equal to 8. Discrete variables can equal a certain value. Here's the weird part. Is it possible to have a foot length that is equal to 8 inches? Okay, so this now, foot length, is a continuous random variable. And the answer to this one is actually technically no, you can't. What? Like, why is that? Well, okay, let's say you have a foot that's real close to 8 inches. If you had enough precision, though, it's probably actually like 8.001 or 7.9999. If you measure enough decimal spots, there are just basically an infinite number of possibilities. If you start allowing like 8, 9, 10, 11, 12, a bunch of decimal spots like this, think about how many possibilities there are. What are the odds you're exactly 8.0000000 forever? Like, it's probably not exactly 8. The reason for that, again, is you basically have one, so 8 is one possibility out of an almost infinite number of possible options. So the idea that you actually equal any certain option is going to be basically rounds to 0. If you have an infinite number of possibilities, the probability that you equal a certain possibility is going to be 0. That's a really kind of weird concept for kids to wrap their heads around. If you have something discrete, you can equal an actual value, like with foot shoe size right there. But if you have a continuous variable, you can't equal a certain value because there are just an infinite number of possibilities, and it rounds to 0, basically. So when we figure out probabilities for continuous scenarios, we don't look at equals. We look at ranges of values instead. So if I take this chunk of possibilities from 7 to 8 inches long, that we could do. So we'll always look at continuous probabilities in like a range. Okay? How many possible foot lengths are there? There are an infinite number of possible foot lengths if you take enough decimal spots. So how can we graph something with an infinite number of possibilities? We'll use a density curve. Okay, you can't graph every single last possibility, but if we're looking at things like foot length and maybe 8 inches is relatively common, you could have lots of people who are in the 8 range, and then we have like less so. I made that look sort of normal. It doesn't have to be. It could be something where lots are popular on this side and less are popular on the other. You would use a density curve like this. So how do we find probabilities? We always do it in chunks. That's not a mathematically sound way of doing it, but basically we'd find, what's the probability from here to here? And the way that we do that is by finding the area under the curve. Okay, so for a continuous random variable, this is a weird point right here that gets kids tripped up. The probability that x is less than a is the same thing as the probability x is less than or equal to a. In our last lesson, I made you do a problem. I think one of them was like x is greater than 3, and one was x greater than or equal to 3. And those obviously had 2 different answers because we added different parts of our table together. One of them wanted 3, one of them didn't. But if your variable is continuous, the chances of it exactly equaling 3 are 0. So it doesn't matter if you put the line underneath it or not. You can go the same answer either way. Okay? So that is a little bit weird to think about, but they are the same in a continuous situation. So maybe some of this is like out there confusing, like you're not really sure what's going on. This will actually end up being mostly fine for you guys because in AP stats, we don't know that many continuous random variables. Our most common one that we know is the normal distribution. So basically, when I want you to practice doing something with a continuous distribution, we use the normal curve because it's the only one we really are good at right now. Okay? So these problems end up being pretty easy and almost completely just review mode because you're going to end up doing a normal CDF or an inverse normal like earlier on in the class. So They say that the weight of 3-year-olds is approximately normal. So X is going to represent the weights. The mean is a 30.7. So we have a 30.7 for the mean, and the standard deviation is 3.6. So sigma of X is 3.6. Find the probability that a randomly selected 3-year-old weighs at least 30 pounds. So 30 would be somewhere over on the right side of the mean of 30.7. At least 30 means everything greater than a 30. It really is just a matter of doing a normal CDF. You draw your picture. My lower bound is a 30. My upper is a big number. My mean is 30.7. And then my standard deviation is 3.6. And then we can just use the command on our calculator like we would do earlier on in chapter 2. So I would do normal CDF, lower of 30, upper of big number. I do a 30.7 and then 3.6, and it's just going to tell me my probability. So if I do that, it looks like it's about 57%. And if I look at my picture, I have more than half the picture shaded, so that seems realistic here. So the probability is going to be 0.577. If this was like a free response question, I would do like a whole fancy answer and restate the question. And the probability that a randomly selected 3-year-old weighs at least 30 pounds is this. But for the purposes of the notes right here, you guys should already know how to do that. All right. So find the probability that a randomly selected 3-year-old weighs between 25 and 35. Well, again, that was a really bad line. 30.7 was my middle right here. Now I care about 25, which is like here-ish, and then 35, which is over there-ish, and my standard deviation is still the 3.6. I think it was 3.6 from before. Yes. So it's just another normal CDF for this problem here. You would just do a normal CDF with a lower of 25 and an upper of 35. And then 3.6 standard deviation, I got 0.827. So when you write these out, make sure you label up your normal CDF commands. So lower 25, upper 35, mean 30.7, standard deviation 3.6, and we got 0.827. Okay. Last problem here. If probability that X is less than K is 0.8, find the value of K. It's the same sort of thing we would do in chapter 2. It's just doing it backwards right here. This time they are telling you that the area from a given point, so K would be somewhere over here. This area in purple is a 0.8. That means we're going to do an inverse normal since we know the area right here. And again, it doesn't matter in a continuous problem. This could have said less than or equal to, and it would be the same exact answer. So if I set this up with an inverse normal and an area of 0.8, mean 30.7, standard deviation 3.6, the value for K is 33.73. Naturally, again, you would show your work if this was an actual test. But basically, continuous random variables, the only one we know about right now is the normal distribution. They can also make you do problems with something called the uniform distribution. Uniform just means it has the same height everywhere, though. So it's at making you literally do math on a rectangle where you know that the area has to be 1. So you can do problems with rectangles too. But that's really all the continuous variables we know about right now. So these problems end up being not too bad to handle.